Okay, so here's where we were last time. We were talking about change of variables. Specifically, there's a nice application of change of variables, really nice application of change of variables, to something that I call symmetry theorems for double integrals and triple integrals that we're going to talk about here. They're all rip-offs of this old theorem from single variable calculus that comes up from time to time, I suppose, but it's not super common in single. I don't know. Like I say, that shows up here and there. But the point is, there's a version of this theorem in multivariable context, and those are extremely useful. So now, in order to make the analogy, I've got to define some tools, some concepts. So here they are. We're going to define in R2 first. First thing I have to do is talk about a reflection over a line. So it's exactly what you think it is. It's this, right? If you've got a line and you have a point here, then its reflection is, well, it's where that point would see itself in the mirror if that green line were a mirror, right? Like I say, it's exactly what you think. Okay. All right. With this idea of reflection, we can talk about what it means for a set to be symmetric over a line. Now, again, this is also exactly what you think. Let's draw a picture. A set that would be symmetric over this line would be something like this, for example. Forgive the artistic imperfection there, but you see what I'm getting at. It's symmetric over the line. And the way we're going to quantify that is we're going to say, look, anytime you pick a point in the set, the reflection must also be in the set. Right? And anytime you have a point that is not in the set, then the reflection must not be in the set. So we need a point and its reflection to always either both be in the set or neither is in the set. Now I leave it to your sort of geometric intuition to see that conjures a pretty good definition of what it means to be symmetric over the line, like this. Right? Okay. All right. Okay. Next thing we want to talk about, I want to generalize this idea of a function being odd. And remember, this was a definition of odd that we had in single variable calculus. If you put the negative input into a function, then you get the negative of the output. Right. Okay, so the way we're going to generalize this to a two-dimensional setting is we're simply going to replace this idea of negative with the idea of reflection. And I'll point out, just for your consideration, that when you have in the real number line a point x, you could think of its negative x as being a reflection over the origin. Right? So saying that I want to take the idea of a negative and replace that with the idea of a reflection, well, not such a stretch. This really originally even was kind of a reflection on its own. Okay, so that being said, the generalization becomes that a function on R2 has odd symmetry over the line if when you plug in the reflection of a given input point, you get the negative value of the function. Okay, all right. So with these definitions in mind, let me not get ahead of myself. Analogous definitions in 3 dimensions. Arguably even more natural, because if you think about reflection through a plane really is like a mirror, because most mirrors that we look at are planes, right? Funhouse mirrors at the circus aside, right? So if you have a mirror, and here's you. It's a huge mirror. But anyway, you're looking at yourself in this mirror. You're going to see your reflection like that in the mirror. It's very, very physically sort of familiar concept. Okay. All right. So then likewise for the definition, symmetric over a plane or symmetric through a plane, if points and their reflections are either simultaneously both in or both not in the set. And odd symmetry, again, exactly what you would think. Reflect the input, you can negate the output. Okay. All right, so with those definitions in mind, here are the big theorems. I'm just going to state the theorems first. Here's the first one. If you have a domain that's symmetric over a certain line, domain for an integral, and if you have a function that has odd symmetry over the same line, right? So this is conditions on the integrand and on the domain for a double integral. These two conditions are met. Your integral is 0. No slicing or dicing, no anti-differentiating. You just walk away. Integral is 0. And it's pretty sweet. The reason why I think this is pretty easy to see is that I'm going to prove this in a different way momentarily, but an easy little bit of intuition is if you look at your symmetric domain. So again, here is a symmetric domain. Then when you chop this up into little pieces, you could chop it up into a little piece over there, and there's going to be a corresponding little piece over here, and the value of the function here versus here, these are negatives of each other. So the term in the Riemann sum that you're adding up for that piece and the term that you're adding up in the Riemann sum for that piece, well, they have the same little areas. The values of the function are exact negatives of each other, so those products are exact negatives of each other, and they cancel in the summation. And because the domain is symmetric, every piece on the one side of the line cancels with another piece on the other side of the line in exactly this way, and it's just everything cancels in a puff of smoke. Okay, so really plausible, I think. Likewise, in 3 dimensions, if you have a domain that's symmetric through a plane, and if you have a function that has odd symmetry over the same plane, then again, your integral is 0. Boom. Right? No slicing and dicing or mincing or whatever the terminology is, and certainly no anti-differentiating. Just, boop, gone. Okay. All right. Fantastic theorems. Again, I'll remind you, in a past life, right, my second major in physics, I did loads of integrals. Those of you who are engineers are looking forward the next few years of doing loads of integrals, and then likewise probably continuing into your careers. And I did so many triple integrals in my physics major. And the world is full of symmetries, as it turns out, right? And no surprises, right? Yeah, lots of things are highly symmetric. And so these opportunities arise very routinely. And being able to just say, 0 by symmetry, big time saver. Huge. I think these symmetry theorems are among the least appreciated integration techniques that I'm aware of. They may be the least appreciated. So, anyway. All right, now we're going to prove these results. First, I have to make an appeal. I don't want to prove this rigorously. I think this is sufficiently geometrically satisfying why should we go into the details? But if you look at a reflection, think about a reflection as a change of variables function. The Jacobian determinant has absolute value equal to 1. And my appeal there is don't forget what that Jacobian determinant is. The Jacobian determinant is a stretching factor, right? It's a comparison between, areas that come out versus areas that go in. Well, if what you're talking about is a reflection, how you reflect areas over a line, well, when you reflect an area over a line, it doesn't change the area. Right? I mean, highly plausible. Again, funhouse mirrors aside, when you look at yourself in the mirror, the image that you see in the mirror is the same size as you are. Right? So I think this is highly plausible. Okay. And with that in mind, here's how we prove our symmetry theorems. It's very quick and convenient. I'm going to do this just for 2 dimensions. Here's the integral we want to compute. I'm going to show that this is 0. Step 1, we have a symmetric domain. Symmetric means that it is its own reflection. So I can change the integral like that. Next step, I'm going to use change of variables. There's change of variables. Notice I'm taking an integral written over an image, and I'm rewriting it as an integral over the pullback, namely the pre-image. Now, this step might be a little easier to see if I change the dummy variable. I have the dummy variable here as being x. Let me change the dummy variable to u. Right, and point being that we have in this change of variables function here, we have x equals r of u. Different dummy variable makes it look a little bit more familiar perhaps, but I emphasize it's just a dummy variable. It doesn't really matter. I could call this Q or P or Bob or anything, and I'm calling it X again just because it doesn't matter. Okay. All right. So when you do a pullback, don't forget your stretching factor. There it is. By the way, quick note, our stretching factor we just agreed is 1. Okay. So change of variables, let's take a moment to recognize change of variables is an essential tool in this argument that we're about to make, we're about to finish. Yeah, right. Okay. All right, well, now again, our other assumption about our situation is that the function has odd symmetry over that same line. Right. And so I get that minus sign. I can pop out that minus sign like this, and lo and behold, this integral is its own negative. Therefore, this integral must be 0. Right? Isn't that fantastic? It's a lovely little argument. Okay. So easy to prove the result with change of variables. Okay. Now, I guess let's go to examples. Okay, so here we go. Let's start with this first example. We want to compute a double integral of this function over the unit disk in the xy plane. Now you'll notice there are lots of lines of symmetry of the unit disk. By the way, notice the question did not tell us what line of symmetry to use. In fact, the question did not tell us to use symmetry at all. This is another very natural sort of state of affairs. When you encounter an integral, and I'm going to say the real world, by which I mean your engineering futures, right? It's not going to come with a label on it that says, here, use symmetry to compute this, right? You have to be on the lookout to identify opportunities to use the various tools in your toolbox. Symmetry is no exception. So anyway, we're going to make the choice here to use a symmetry argument because, fingers crossed, it's going to work. But we also have to decide what line to use. Okay, so the unit disk, a huge number of options of lines of symmetry for disks, highly symmetric. Okay, so what about the function though? Does that function have odd symmetry? And more to the point, what line, if any, what lines, if any, over what lines does this have odd symmetry? Okay, so I'm going to start off with the right answer, and I'll tell you how I got to that in a moment. But we're going to look at reflections over the x-axis. And here's a picture of a reflection over the x-axis. There's our xy plane. The x-axis is like this. And I appeal that if you have a point x comma y, then the reflection has the same x coordinate but the negative of the y coordinate. So the reflection over the x-axis is like that. How are we doing? Is everybody on board with that suggestion? Notice there's a seeming sort of like unexpected. A lot of people think, oh, if you're reflecting over the x-axis, shouldn't you have a minus sign on the x coordinate? Nope. Look at the picture. Right now, so this is a situation where you have to just observe what it unavoidably has to be, realize that it's kind of the opposite of what you might expect from a sort of a symbolic, kind of superficial approach, and just be on the lookout for this in the future. Just like I say, it's a very common landmine for students to step on. So be careful. Always think it through. Think through the picture. Think about the coordinates. And make sure to get it right that the minus sign goes there. Okay. Analogously, if you're reflecting over the y-axis. Okay. Okay. So if that's what a reflection is, now let's see if this function here has odd symmetry. We're hoping that this function has odd symmetry. I need to take that function, I need to plug in the reflection and confirm that I get the negative. So I am literally going to take this reflection, x negative y, plug that into the function, right? Do the appropriate algebra. There's the coordinates of that reflection. Crank it out and observe that, yep, sure enough, as required, we do get that minus sign there. So the image of the reflection is the negative of the original image. We have ourselves an odd function. Okay. All right. Done. Right. We have a line over which the domain is symmetric and the function has odd symmetry. Integral is equal to 0 by symmetry. Everybody happy with how that played out? Okay. Yeah. So how did I choose? Where did I come up with this choice to use the x-axis? Why didn't I use, for example, the y-axis or the line y equals x or some other wacky line? All of these are symmetry lines for the domain. What made me pick this particular line, the x-axis? And let me sort of reverse engineer sort of the strategy here. I know I want there to be a minus sign here in the calculation. And so let's think it through. What could I do to these coordinates to make a minus sign show up? Right? And I'll make the quick observation. If I were to stick a minus sign on the x, then that would be useless, right? Because it's about to get squared. So putting a minus sign on that would not result in the minus sign in the output that I need. Okay. On the other hand, if I can figure out a way to stick a minus sign on the y-coordinate, then that's a minus that's going to get cubed, and negative 1 cubed is negative 1. That gives me the minus that I actually need, right? So my first thought on this problem when I was writing out the solution is how am I going to get a minus sign where it will do me the good that I need? And so I realized here, okay, I need to get a minus sign on the y-coordinate. And then I just thought to myself, okay, well, if I need to reflect in such a way that I negate the y-coordinate, what line do I reflect to make this the formula for the reflection? And you can just see right here in the picture, the way you turn xy into x negative y is to reflect over the x-axis. Everybody see the argument there? You can totally just kind of work backwards through how you want it to work out to identify, in this case anyway, what your symmetry is. Okay. All right. Yeah. Okay, so moving along. Let's do another example here. Let's suppose we want to compute, same function, you'll notice. Same function. And let's suppose I want to compute an integral over the triangle that has vertices at these 3 points. And let's go ahead and draw a quick picture of that. Quick picture is those vertices are, let's see here, 0, 1, negative 1, 0, 1, 0. So here's our domain. Our domain looks like that. And here's the landmine that students also often step on. A lot of students say, I see a symmetry. This domain is symmetric. And our domain is symmetric. Our function has odd symmetry. Integral equals 0 by symmetry. And they walk away, turn the page. Psyched. Right? Okay. And it's wrong. This is a very easy mistake to make. Here's what the mistake was. The domain is symmetric over the y-axis. The function has odd symmetry over the x-axis. Those are not the same line. It has to be the same line. Right? You can see in the argument why it's got to be the same line. Right? When I do this reflection, it's through that pullback that I have to get this minus. It's got to be through the same reflection. Right? So, got to be the same line. Again, you'll notice that in the statement of the theorem. Same plane if you're in R3, same line if you're in R2. Okay, so this not only is the answer wrong here to say that integral is equal to 0. Not only is the answer wrong, but the argument, worse, the argument is wrong. The argument makes no sense. Just noticing, can we use a different line? We do have that symmetry of the domain, but it's over the y-axis. That reflecting over the y-axis gives you a minus sign on the x-coordinate, and we've already kind of talked about how that minus sign on the x-coordinate just gets squared away. And so it does not give you odd symmetry. Right? This function is not odd over the symmetry of the domain. So, can't do it. Okay. Be really, really careful with this. Again, it's a very dangerous scenario. And let's talk about how this plays out, strategically on an exam. Right? Suppose this were the question. Suppose you make the invalid symmetry argument. Not only do you get a wrong answer, your argument's not valid. And furthermore, your argument is nowhere even in the direction of a valid solution to this question. A valid solution to this question, to compute this double integral of that function over that triangle, doesn't have anything to do with symmetry. You got to slice it, dice it, do the antiderivatives. So nothing that the student has written on the page is relevant to the solution. I can't give any partial credit for it. Nothing's relevant and true. Okay, so I hope you all see this is a very, very dangerous thing. As much as I love symmetry arguments, big fan, right? Apply them carefully. Think it through. Make sure that your argument is legitimate before you do it. Okay. All right. Now I want to talk about one more thing about symmetry theorems before we go along. And that is there is a strategy that could be made, test-taking strategy. I've employed this myself with profit when I was an undergrad. The strategy is if you're out of time, you got 10 seconds left. There's an integral here. Oh my gosh. Equals 0 by symmetry, and then you just turn in your paper. Right? There is about a 20% chance or so. I mean, it depends on the context, right? But it would not be at all unrealistic. It is routine for, in fact, the integral, to be 0. Symmetry is the way to see it, and what you've written down is technically kind of true. Right? So this is the, what they used to call a Hail Mary pass in football, right? It's like you got no other options, right? Equals 0 by symmetry, and keep your fingers crossed and hope you might just get lucky, right? So again, I did that when I was an undergrad. I scored a couple times. Anyway, I feel like that the credit that I got for that was completely undeserved, right? I was wild guessing. I didn't have time. I had 10 seconds, right? I didn't have time to think it through. I wrote it down because there was a possibility it might work. I did not actually understand about that specific integral. And so I kind of feel like those instructors were being a little careless with giving me those points. And so in my classes, I do focus on reasoning. Right? And so you need to persuade me that you actually understand the symmetry argument before you can actually get that credit. So here's what I want to see on an exam. If you want to use the symmetry argument, either double integral or triple integral, you've got to tell me that the domain is symmetric. Let me be more, put this in the right order. You got to pick your axis. You got to pick your line. Over what line are you going to apply a symmetry argument? That's the first thing. Give me the line. You've got to state that the domain is symmetric over that line, and you must be correct about that. You don't have to prove it. Geometrically, I think if its shape is symmetric over a line, I think that's geometrically fine. But you do have to state it, right? Because you have to persuade me that you understand that symmetry of the domain is actually important. So stating it is a way of indicating that you realize it matters. Right? No proof required. And you, like I say, you have to be correct. You can't just assert symmetry of something if it isn't symmetric. Okay. Let's see here. You have to show. You have to give me the formula for the reflection over that line, and then you also have to demonstrate algebraically that the function has odd symmetry. Right? Because this isn't obvious. That a function has odd symmetry over a certain line, really not obvious. Right? So that I do want to see. So these are the four things. You got to give me the axis. You got to state correctly that the domain is symmetric. You got to give me the formula for the reflection over that line, and you've got to give me the argument, the algebraic argument showing the function has odd symmetry. And then, spike the football. Yeah? Everybody understand the rules? Okay. It's still a big time saver compared to actually slicing and anti-differentiating. Okay. All right, there's a couple more examples here. I want you all to read these examples. Here is a really, really bad domain over which, if you want to do an integral, it gets pretty brutal. But if you make a clever choice of a line of symmetry, there, write down the formula for the reflection over that line. You can notice quickly that the function has odd symmetry, and we win. Integral is 0 by symmetry. Now, read through the details, make sure you're good with that. And likewise, another cool argument here, and I want you to take a look at that one as well. Okay, last comment before we go on to the next section. Be warned that it is now open season on symmetry arguments in integrals. So what I mean by that is I will, in the exercises going forward in this book and on all future, in the remaining midterm and the remaining final exam, I may put integrals for you to compute that would be completely intractable by any method other than a symmetry argument. And they will not be announced necessarily. They might be, but be aware, they very likely will not be announced. So you've got to be on the lookout. I want y'all on your toes. Right? It's very valuable to be on your toes looking for opportunities to use symmetry arguments. So in these homework exercises, and conveniently, I have already forgotten which ones, but there are multiple integrals that you're being asked to compute here, which would be brutal unless you use a symmetry argument, in which case they're really easy. So heads up. Be on the lookout. All right, another integration technique. So this next section, integrals and coordinate system. Not really a new kind of integral. It's going to feel kind of like it, but it isn't. This is just a technique for computing. The first observation I want to make is that we have a bunch of coordinate systems. You all remember polar coordinates, cylindrical coordinates, spherical coordinates. And you can use them as change of variables functions. It's a really convenient tool in a very large number of circumstances. So here's an example. Here's our polar coordinates formulas. Right? If you give me an r and a theta, here's the formulas for x and y. And notice, it's a function from R2 to R2. 2 numbers in, 2 numbers out. How about that? Right? So we can just reinterpret. Instead of thinking of these as, conversion formulas for coordinate systems, we can just take the exact same formulas and say that is a change of variables function and proceed with the process. So, for example, here's a domain. I'm going to call this an undesirable domain in the xy plane, because whichever way you slice, you've got to solve either for y as a function of x or x as a function of y. Either way, there's going to be a square root involved. Right? And square roots on the inner bounds means square roots in your outer integrand And square roots in an integrand is very often hard. Okay. All right, so here's the thing. I claim that this undesirable domain is the image of a much more desirable domain over here in the r theta plane, doing a pullback through our polar coordinates change of variables function. And let me just persuade you that this is the case. Let's look at this line segment right there. That line segment has theta equal to 0 and r goes from 0 to 1. And in the xy plane, there's theta equals 0, r goes from 0 to 1. Now let's look at, let's see here, this line segment here. That's r equals 1. Theta goes from 0 to pi over 2. Okay, so on r equals 1, theta goes from 0 to pi over 2. Etc. This line segment, theta is pi over 2. R goes from 0 to 1. That's that. And this whole edge here, that whole edge is on the line where r is equal to 0 on that entire line. And with r equaling 0, it doesn't really matter what theta is doing. So that whole edge pinches down like so. And so this polar coordinates change of variables function takes this rectangle and gives as its image that quarter disk. Everybody on board? So we have an opportunity for a pullback. Right, I can take whatever integral I might be interested in on this domain, I can pull back and turn it into an integral over a rectangle. So, sweet. Let's proceed. Now, I do have to compute the stretching factor. Here's our computation of the stretching factor. You got to compute the Jacobian. Right, the Jacobian of that polar coordinates change of variables function. It's a few partial derivatives. Y'all know how to do partial derivatives. It's a good exercise. Go through and confirm that you can reproduce that is the Jacobian. Right? Crank out its determinant, and what you find is that the determinant is r. And as long as you make the promise that you will only choose positive values of r, which is not much of a concession, right? I mean, we like positive values of r anyway. Negative r's are kind of weird and confusing and counterintuitive. So just promise to do what you would prefer to do anyway. Always choose positive values of r, and your stretching factor is just r. Absolute values have already disappeared. It's a lovely answer. It's almost the best answer we could have hoped for. Right? So there's your stretching factor, and pull it on back at this point. Right? So the integral in the xy plane, don't forget that x and y are established functions of r and theta. That's that whole r cosine theta, r sine theta business right here. Right? Don't forget to put in your stretching factor. Dx dy is stretching factor times dr d theta, and that stretching factor we just computed is r. And here you go. We've pulled back the integral. Here's an integral in the r theta plane. Don't forget about that r sitting there. A lot of students kind of forget, for whatever reason, just kind of ignore that r. That r is important. Right? But this is an integral over a rectangle. Look how awesome the bounds are. No square roots. We've successfully gotten rid of square roots. And I'm going to call that a big win. Now, a standard complaint at this point is, yeah, but you got rid of square roots, but you introduced trig, and is the cure worse than the disease, right? No, the trig is highly preferable to square roots, because trig has a bunch of trig identities that you can use, and trig integrals are definitely easier. By the way, those of you who recall trig substitutions from way back when, a common way to deal with the square roots that we would have encountered in this integral is to do a trig substitution and introduce trig voluntarily as an attempt to get rid of those square roots. Okay. All right. So, yeah, so there you go. So there's we're using polar coordinates as our change of variables function. Notice, by the way, this calculation will always work out the same. As long as you promise to only use positive values of r, your stretching factor will always be just r. And so, therefore, your dx dy will always turn into r dr d theta. Now, along these lines, I have a bit of advice. This is strategic advice. This expression, r dr d theta, I encourage you to just memorize that expression, r dr d theta. Whenever you want to use the polar coordinates formulas as a change of variables function, dx dy will always be r dr d theta. Just go ahead and have that locked and loaded, memorized, and boom, just write it down, r dr d theta. You don't have to derive the Jacobian determinant every time. That'd be silly. Cool. Oh, one other related bit of advice. When you write down your polar differentials, another classic mistake that students make is to write down the dr d theta and then think, okay, those are my new differentials. Now let me go over to this huge distraction of trying to find the bounds. What's the shape of the pullback and what are the bounds and polar coordinates, etc. And then, having gotten that all figured out, then they forget to go back and put in the stretching factor of r. I cannot tell you how often I see this. It's shockingly common. So the way that I think you can best combat this is don't write down dr d theta by itself. Just don't ever do it. Just always write down the r as you are writing down dr d theta for the first time. Think of this as kind of a single thing, which it is, by the way. That is dA. It is a single thing. In fact, it's kind of unnatural to write down dr d theta by itself. What is that? That's not immediately related to something from our original integral. So write these down simultaneously, and it cuts down on the odds that you'll forget. Everybody see the idea there? Okay, so have fun using this change of variables function. It's really, really useful. Ditto with cylindrical coordinates, by the way. Here's a reminder what cylindrical coordinates look like. And, you can write down the formulas and you can take the Jacobian determinant. And again, I think this is a healthy exercise and I hope everyone will do this. Make sure that you can reproduce that is the Jacobian matrix for the cylindrical coordinates change of variables function. Just thinking of the coordinate system as a change of variables function. Crank out the determinant, algebra, and no surprise, it turns out again to be r with the same restriction that we have to require r to be positive, which we want to do anyway. Okay, I say no surprise because, really, cylindrical coordinates is just polar coordinates in the xy plane combined with, let's add a z. It's the same z in both coordinate systems. So all the action of cylindrical coordinates is really happening, kind of, if you will, in the x and y coordinates anyway. So it really is, for this purpose, cylindrical coordinates really is just like polar coordinates with an extra z dimension. Okay, so again, go for it. Right? Use this as a change of variables function. Here's an example of a pullback domain. I claim that this, half of a cylinder, right? Half of a solid cylinder. That pulls back very nicely to a rectangular box. And let's think it through real quick. Let's look at the various different faces here. So let's think about that face right there. That face is where theta is 0. Goes to that. Right. Theta equals 0. Z ranges over certain values. R ranges over certain values, 0 to 1, I guess. Okay. All right, so that goes to that. Let's see here. Now, what happens as I move sort of along like that? Well, each one of these green slices that I've drawn here in the cylindrical sort of pullback space represents a fixed value of theta. with, again, z goes up to a certain height, r goes out to a certain radius. Different fixed values of theta, but otherwise the same. Like that. And so that purple rectangle in the XYZ space, it's like it's on a hinge on the z-axis, and it just kind of rotates around until you get to the end where theta is equal to pi, which of course is there. Yeah? Okay. All right. So if you had an integral on that domain, you could say, I'm going to use cylindrical coordinates as a change of variables, and it will pull back then to an integral on a nice rectangular box. Okay. All right. Details are here. Here. There you go. Okay. Spherical coordinates. Morally, same strategy. Different details, of course. But here's our spherical coordinates formulas, our spherical coordinates conversion formulas. Y'all recognize these from chapter 1. Let's see here. It's either 1 or 2. I guess it's 2. Anyway, y'all recognize these from long ago, right? Several weeks ago. Formulas for x, y, and z in terms of rho, phi, and theta. Don't forget, spherical coordinates looks kind of like this. Right, there's the rho, phi, and theta. Make sure to keep it straight which one's phi and which one's theta. It's real easy to get that backwards. You can view this as a change of variables function. Again, this is sort of the new point of view. We're going to, instead of thinking of this as just a new way to describe points in space, we're going to think of it as those formulas give me a function from rho, phi, theta world into XYZ world. Right? And as a change of variables function, here's the computation of the Jacobian determinant. Now, I just skipped a tremendous amount of algebra there. I think it is a healthy exercise for the reader to fill in those blanks. I want to encourage everybody to do that. It's a little tedious, I will recognize, but this is a healthy, everybody should do this once in their life kind of a deal. I did mine. Right, y'all got to do yours. So it's going to take you several minutes, but it's good practice. By the way, it's good practice in being on the lookout for and being able to take advantage of Pythagorean identities. Sine squared plus cosine squared is going to come up a lot. Look at all the terms in here. It looks like a nightmare. Can you imagine taking the determinant of this monster? There's going to be sines and cosines just everywhere. The Pythagorean identity is going to come in and hack through huge segments of that. And the final result is that this Jacobian determinant is rho squared sine phi. Okay. Now, a lot of students misunderstand what the deal is with the absolute values. With polar coordinates, we had to promise that r would be positive, and then we could ignore the absolute values. Well, in spherical coordinates, isn't rho kind of like the r? Isn't there an analogy there of some sort? And so shouldn't it be rho that I have to promise to be positive? And then I can get rid of the absolute values. And you can see here that that's nonsense, right? What would happen if rho were negative? Nothing. It gets squared. Who cares what rho is? Rho could be positive, negative. Who cares? It's all good. So what we have to worry about in this expression is how do we know that sine phi is positive? Right? That's the thing that totally could be negative, and if it were, then our absolute values would become a problem. Right? So the way we ensure that is not negative is just we require going forward, if you want to use spherical coordinates as a change of variables function, you have to keep phi between 0 and pi. And I remind you, those are the values of phi that we want anyway, right? Again, we're being required to do what we were hoping to be able to do in the first place, right? It gets super weird. Y'all remember way back when we were seeing spherical coordinates the first time, things got real confusing when you were like, okay, let's lean backwards with phi being negative, and oh my gosh, it's just really disorienting. So these are the easy values of phi. You are simply required to use only the easy ones. So I think that's funny. Okay, that being said, you choose these values of phi. This is all positive. The absolute values can go away. And your nice result then is that dx, dy, dz, dv from your original integral is this expression. Please also memorize this expression for dx, dy, dz. It's rho squared sine phi d rho d phi d theta. It's a mouthful, right? But memorize that. Always write that down all at once, please. It would be super unnatural to write these differentials down. I know it feels kind of right to, well, let me get my differentials down first, and then I'll go off and do other things. It's a very common cause of students just oopsing this essential factor of rho squared sine phi. Right? So write these all down all at once, all together, as a single thing, and because they are. In fact, this is dv for the original integral. So it is a single thing. Write it down as a single, all at the same time. Okay. And then let's think about the slicing. I have a picture. Yeah, here we go. Let's look at this slice here and think about, what do these things look like? Let's look at this slice here. That's where theta is 0. Theta is 0. Be like that. Yeah. Okay, yeah, but wait a minute. On that theta equals 0 slice, phi goes from 0 to pi over 2. There's phi equals 0. Here's phi going down to pi over 2. Right? And then phi ranges from 0 to pi over 2 over each value of rho. Rho goes from 0 to 1. So in each one of these directions, rho goes all the way out to 1. So all together then, messy picture, but all together this has as its image that little quarter disk in the xz positive x slice of that half ball. Everybody on board? See how the geometry works there. And then again, think about what happens as you raise theta up like that. Well, then you're going to just get half disks that are kind of going around, right? And in fact, if you go all the way up to theta equals 2 pi, it means this thing goes all the way around to where it started, and you get the entire half ball. Yeah? Everybody see how that works? So we've done a pullback of our domain. The pullback of this half dome, and again, imagine the nightmare of the integral if you were to do this in rectangular coordinates, right? There'd be square roots everywhere because the slices are circles and then the slices of the slices make circles, and oh my gosh, square roots everywhere. Whereas doing the pullback, we've pulled that back to a rectangular box and the bounds are constants. And you can see that in how this integral worked out right here. Again, details y'all can notice on your own, but there's that rectangular domain in rho phi theta world. Okay, again, the structure of this calculation, dx, dy, dz, rho squared sine phi d rho d phi d theta. Right? Don't forget to plug in the actual formulas for x, y, and z. X, y, and z are all, and admittedly, there's a lot of trig in there, and that is a little annoying. Right? But you got to plug in for what x, y, and z are. That's just plugging in, though. And I emphasize, make double sure you don't forget your stretching factor. By the way, if you forget your stretching factor, that really is a big deal. The stretching factor is what makes this actually legitimate as opposed to the naive suggestion that I can just rewrite dx, dy, dz as d rho d phi d theta by itself. It's complete nonsense. Wishful thinking garbage if you don't put the stretching factor in there. So it's a very big deal. It's going to be worth a lot of points on the exam to don't forget your stretching factor and make sure to get the factor correct. That's another thing that happens surprisingly often is that students will misremember the stretching factor as like, rho sine squared phi or something, right? Or just rho sine phi. So make sure you memorize exactly what that is. Okay, all right, so pretty much this is how you do integrals in these different coordinate systems. The only thing for me to introduce now is a sort of a point of view, and this is kind of just a matter of how you think about it. So let's look at this picture here specifically, and we've talked about this domain in the xy plane, and then using polar coordinates we can pull that back to this rectangle, and on that rectangle you can see what the bounds are, and that's fine. But I'll point out that as you go through and find out what the bounds are over here, you can actually see those bounds over here also by just looking at the slices. So here's what I mean by that. We've pulled back to this rectangle. Let's look at our slices. Theta goes from 0 to pi over 2. Okay. That's what theta slices look like. We're slicing perpendicular to the theta axis. Those are literally theta slices in our pullback domain. Okay. Yeah, but here's the thing. This little slice right there, we know that corresponds to that right there. And as these slices proceed, you can see what those slices look like as well. And et cetera, et cetera, et cetera, et cetera. It ends there. It ends there. So look, you could, if you feel the need to, I suppose you could actually draw this pullback domain and then in a nice and familiar sort of rectangular fashion find what the bounds are. But it's so much easier instead to say, look, I don't need that picture. I can see right here that theta starts at 0. And I know what theta slices look like. Theta slices are these radial line segments emanating out of the origin. And I can see that theta ends at pi over 2. So the suggestion is just see the bounds on the pullback polar integral. See those bounds in the xy plane by just understanding correctly what theta slices look like. Theta slices look like this. And then you don't need to draw the pullback domain at all. Okay, likewise, now let's talk about the R bounds. On a given theta slice, theta goes from here to there, and then once you found the theta bounds, you fix a value of theta, and then you focus your attention on, well, R starts there where R is 0, and then R ends there where R is 1. And again, that's the familiar kind of, that's how we slice things up. But notice you can see all of that in the xy plane as well. So here's that theta slice that we're looking at. And here's that starting value of R. And now, I can't see the R axis. True. Right? But I know that the polar coordinates of that point include R equals 0. And I know that this is what increasing R looks like. Along that theta slice, this is what increasing R's look like. And then the last value of R is going to be there, where I can just see from the picture R is equal to 1. So again, we don't really need the pullback domain. You can see everything you need to know about the bounds right there in the original undesirable domain, your rectangular coordinates domain. So why draw the picture? So that's the big last step. Just so don't bother drawing your pullback picture. You don't need it. it leaves you open to the possibility that you might inadvertently draw it wrong, or there's a process in figuring out what that pullback domain is. So don't subject yourself to that potential for oopses, and completely unnecessarily so. Right? Everything you need is right here in this picture. Okay, so that's the last point on that. So, for example, let's suppose this is our domain here of a semi-disk. Well, theta starts at 0. Theta slices look like this, etc., and they end there. So theta starts at 0, theta ends at pi. Now, I could draw the pullback domain. It's a rectangle. Sure, I suppose, but why would I? What's the point? Right? I can further see, in addition to those theta bounds, I can see that for a particular theta slice, R starts where R equals 0, and R ends where R equals 1. It's all right there in the rectangular picture. Okay. Here's a less convenient one. Let's suppose that my domain is an offset disk in the XY plane. Okay, well, this offset disk, here's what a theta slice looks like. Again, theta slices are always sort of, rays emanating out of the origin, like that. Where does it start? Where does it end? Well, let's draw a bunch of these theta slices, and how far do I have to go? What's the last? Let me switch to pencil mode here. What's the lowest value of theta until I'm not slicing the domain anymore? And I claim you got to go all the way down to negative pi over 2. Right now, that's just a geometric appeal of anything beyond negative pi over 2, and this is a swing and a miss. There's nothing over there. Right. Okay. So start at negative pi over 2. Whoops. Here's that first slice at negative pi over 2, and then the slices proceed around until, again, looking at it on the positive theta side, they're getting shorter and shorter, cutting off less and less, and that very last slice is going to be at positive pi over 2. Everybody see that in the picture there? Okay, then, for a given theta slice, here's a given theta slice. Well, R starts at that point. That's the origin. R is clearly 0. R ends, now, be careful, at that point. The R coordinate at that point is going to depend on where that point is, right? R is a lot lower over here, and it's higher over there, and then it's lower over here again. R is going to depend on theta. So in order to figure out how R depends on theta there, I've got to write the equation of this circle in polar coordinates. I've got to solve for R as a function of theta. Now, y'all know how to do this. We know how to write the equation in rectangular coordinates. And recall from, again, way back when, multiply it out, plug in the conversion formulas, polar rectangular conversion formulas, and out's going to come an equation that tells you R is a function of theta. And in this case, that's what it is. So a reminder, make sure that you can do this. Make sure that you can convert from rectangular to polar. And likewise, from rectangular to cylindrical, rectangular to spherical, right? You've got to be able to do the conversions of equations from way back when. Okay. All right. So that having been established, looking back at our slicing, on a theta slice, R goes from 0 to 2a cosine theta, which is, where did I write this down? Yeah, here we go. R goes from 0 to 2a cosine theta, as theta goes from negative pi over 2 to positive pi over 2. Everybody good? Yep.
Why is the equation of the circle, like not x minus a squared, like in the integrand, I guess?
Yeah, the integrand, let's see, where is the statement of the question? Here's this. Okay, the statement of the question was that our integrand is f. And when you do a pullback, I mean, the only way the integrand changes is by introducing the stretching factor. Right, so that f comes along for the ride. Here it is. Oh, and I have a formula for f. Here it is. F is x squared y. So there's that x squared y. And then the only thing that changes is we introduce the stretching factor. Yeah, does that make sense? So the domain is the x minus a quantity squared, etc. All that business was about understanding the domain, shape of the domain. Yeah. Right. Okay. So what do slices look like? Let's see here. I'm gonna. Oh, by the way, I got a little ahead of myself here. Yeah, okay, fine. I'll look at this. So how about doing it with your polar coordinates in the other direction? Why not do d theta dr instead of dr d theta? And my answer on that is going to be that sometimes you can get away with that, such as here. This one works out. It's sort of okay if you do your theta slicing on the inside instead of the outside. But it is extremely rare to find a situation where this is actually beneficial. Vast majority of the time, it's either totally equivalent. Look, the bounds are constant. You could totally do this. It doesn't matter, right? Totally equivalent, or much worse to do it this way, right? D theta dr is very rarely a good idea. And just to show you what you might encounter, here's how a integral worked out. With you'll see the d theta dr here. We're doing it in the unsuggested order. And check this nightmare out. But now we've got inverse trig functions in our inner bounds, which means we're going to have inverse trig functions in our outer integral. Oh my gosh. Right? Nobody wants this. Right? So just don't ever do that would be my advice. If you absolutely blindly never do d theta dr, it'll cost you almost nothing. It may cost you absolutely nothing ever in your life. And there's a slim chance that it might someday, maybe, I doubt it, possibly make you miss out on something. So in Math 212, there won't be any examples where this is the preferred order. Okay, so let's move on to this same perspective in cylindrical coordinates. Again, we could draw a pullback domain, but that's hard to do. How about let's just see what the bounds are in rectangular coordinates by just knowing what slices look like in these different coordinate systems. So here's what a z slice looks like. Here's what a theta slice looks like in cylindrical coordinates. Constant value of z, constant value of theta. That's what your slices look like. You can just see the bounds by looking at the appropriate kind of slices while you're looking at your rectangular domain. The R slices are a little funny looking. Right? That'd be a weird kind of a knife to cut in a circle like that. So it's a little awkward to think of R as being a kind of a slice. So my suggestion on that is don't do your R slices first. This is what your R slices will look like. And so don't. Right? So, for example, do your Z slices first. If you do your Z slices first, then an R slice after that would just be a circle. Or, even better, if you do your Z slices first and then do theta slices, well, your theta slices will just be little line segments. That's what a theta slice of your Z slice would look like. And then R, starting value, ending value, and you never have to deal with this kind of ugly slice. Okay. All right. So your two reasonable choices in cylindrical coordinates are to do R, dr, d theta, dz, or R, dz, dr, d theta. always pick one or the other of these. There's effectively never any reason to do anything other than one of these orderings. Notice that I am keeping the dr d theta together and in the appropriate order. Right, dr d theta. Don't ever do d theta dr. Then there's only two possibilities for where the dz goes, either before or after. Okay. So here's an example. Let's look at this. This as a domain. This is a cone with its upside down cone, sad ice cream cone, right? Dropped sad ice cream cone with the vertex at the top and the base at the bottom, radius 1, height 1. Different ways that we could slice on this, but let's see, how did I do this here? Yeah, okay, so one way to slice this would be to look at your z bounds. Z starts at 0, z ends at 1. Right? So I'm doing dz on the outside, dr d theta on the inside. Don't forget to write down your r. So easy to forget that. So we've got z goes from 0 to 1. Then now for a given z slice, theta starts at 0, goes all the way around to 2 pi. And then for a given value of theta, r starts at 0. R ends at a point there that we're going to have to talk about. Finding out, let's see, what is r at that point? Notice we're allowed to have r be a function of theta and z, and I'm going to leave it as an exercise in understanding equations of surfaces to persuade you that that point, being as it is on, being as it is on this cylinder, and that cylinder has this equation, r is equal to 1 minus z. So think about the rotational symmetries of the cylinder and what it looks like in a cross section, and not hard to persuade yourself that r plus z has to be 1 because the cross sections are lines and details for y'all. Okay, so the bounds then, here we go. Z went from 0 to 1, theta went from 0 to 2 pi, and then r goes from 0 to 1 minus c. How are we doing? Is everybody on board? Everybody happy? Okay. Another nice exercise. What would happen if you did the differentials in the other order? Namely, what would happen if you did put your dz on the inside? How would that change things? You can't do this, right? Because those bounds are not constant. Everything would change a little bit. So that'd be a good exercise to think through. Okay. Spherical coordinates. Same deal. We've seen how to use spherical coordinates as a pullback. Fine. You can think of it as change of variables. No problem. But I think it's easier, highly desirable, to figure out the bounds by not drawing the pullback. The pullback might be hard to identify, but by looking at what the appropriate slices actually look like in XYZ world, and then just think about those kinds of slices to figure out the bounds. These are what the slices look like. These are constant values of the spherical coordinate variables. This is what it looks like when rho is a constant. You get a sphere. This is what it looks like when phi is a constant. You get a cone, a happier cone. Yeah. And then this is what it looks like when theta is a constant. Of course, it's the same theta as from cylindrical coordinates, so that looks familiar. Okay, now you'll notice that multiple of these slices are geometrically unappealing, right? I can't even imagine a knife that would cut a shape like that, right? Oh man, what would be if I had some sort of a domain and if I took a spherical slice through the domain, oh my gosh, so hard to draw, so hard to visualize. So don't do your theta, don't do your row slicing on the outside. That would be very, very uphill road to choose. Right? Likewise, I think that's pretty weird. So I think it's practically always the right answer. Again, in Math 212, I doubt I'll be able to, and I certainly won't be motivated to, dream up an example where the following is not the best choice. But do your theta slicing first. Oh my gosh, for sure, right? Because then your slices are flat. Inside of your theta slices, in other words, next, notice that a phi slice at that point, a phi slice would just be, coming from a cone like that. Inside of that theta slice, a phi slice is just a straight line. Right? So d phi is a very natural next choice to make. And then, of course, after that, d rho, doing your row slices last. You're just looking for starting and ending values, whatever those are. Again, don't forget your rho squared sine phi. So easy to forget that. So with all this in mind, this is the highly suggested order to do your slicing. Always do theta on the outside, then phi, and then rho on the inside. So as we've already memorized it, rho squared sine phi d rho d phi d theta. Always do it that way. Pause for questions. We do an example. Is everybody on board? Okay. Alrighty. So let's suppose we're looking at a ball of radius A centered on the z-axis above the origin, and notice it has radius A and it's sitting a height A above the origin, and so this sphere is actually it's like it's sitting on top of the origin. Right, it's sitting on top of the xy plane at the origin. Okay. All right. So let's start slicing it up. Let's see, what pictures do I have here to work with? Good. Okay. So theta first. Theta starts at 0. Let's think about what our theta slices look like. Our theta slices are going to be these half discs in the appropriate theta plane. That's a slice, right? For what values of theta am I actually slicing up my domain? Well, theta is going to go all the way around 0 to 2 pi. Now, at the geometric appeal, you got to see that from the picture. Our solid here, our solid goes all the way around the z-axis. The z-axis is, you might say, embedded inside of our solid. So you're going to keep getting slices for every value of theta. Right, you're going to get these kinds of slices. 0 to 2 pi. Everybody see that? Okay, so that's one of our bounds. There it is. There's one of our slices looks like. Okay, so now we're going to pick and fix a value of theta. We're going to focus our attention on that theta slice, and now inside of that theta slice, I want to understand the range of values of the next variable, which is phi. All right, now I have an unexpected suggestion here. You don't have to do this. I think this is a really good idea, strategically speaking, anyway. It is hard to really see what we've got here because we're looking at a picture. We're not looking straight on at our picture. We're looking at an angle, right? Because this is an arbitrary value of theta, and so when we're looking at it from an angle, and then we're trying to inside of that then judge what other angles look like. It's just hard to see what angles look like when you're looking at them on a weird angle, right? So my suggestion is redraw this picture. We only need at this point to look at just that theta slice. I no longer have any use for all of this stuff. We'll get there. Other values of theta, right? So let's just focus, since the rest of our attention needs to be on that theta slice, let's draw just the theta slice, and let's draw it looking right at it. So here's that same theta slice here. looking at it, sort of straight at it. This is what you might call the sort of the R-axis, if you will. This is that theta slice. It's this thing here that's going to be too hard to shade in. And now it's just easier to see what phi is doing, right? Looking at this picture, I recall that phi is an angle measured off of the origin. So these are what our phi slices are going to look like, but again, hard to see them there. But over here, just a lot easier to see those phi slices. Oh, whoops, what happened there? That wasn't me. So these are my phi slices. As phi gets, bigger and bigger, and you notice that as I approach pi over 2, the phi slices kind of dwindle out to nothing. Right? And so pi over 2 is our last phi slice. Of course, 0 in this case is our first phi slice. So like I say, I think it's easier to see on this picture here. Is everybody good? Is everybody happy? Okay. So like I say, it's an extra picture to draw, right? And there's a cost there, but I think it's worth it to make it easier to visualize what's going on. Now, let me give you a warning, a very common mistake. Again, I see this all the time. It's easy to misunderstand. Phi is measured from the origin. Students very often will conflate the idea of the origin with the idea of, the center. That's the middle, the center of whatever you're looking at. And a lot of students will misunderstand phi as being this. And that's wildly wrong. Phi is not measured from the center of whatever you might happen to be looking at. Phi is measured from, I went way over time. Sorry. Phi is measured from the origin specifically. So if you have your wrong center, you're going to get the wrong range. You're going to get 0 to pi. Make sure not to step on that landmine. And we'll draw it right here for today. So see you tomorrow.